This is a quick video over the potassium channel. So here's the channel right here, and we will have some sodium ions, which are those, or potassium ions, which are those, and sodium, which are these little green guys. And it would seem like this green guy could easily fit right through this channel. But that's not the case. You gotta remember that these are charged particles, so they are positively charged. And what are they floating around in? Well, they're actually floating around in water, so we need to add water to these. So we'll add some water. Now we have water added to them. And we're going to say that you need 4 oxygen atoms for every ion. This is an oversimplification, but we're just doing it just to show how it works. So now, this sodium, it needs to have 4 oxygens attached to it, and it can't easily fit through here. What happens is, water actually can't go through this tube. Water cannot go through. Can't go through. And the reason is because of these oxygen atoms right here. They prevent water from going through. So if water can't even go through, what can? Well, it's actually these sodium ions, or these potassium ions can. So if we had a potassium right here that just randomly bumped into it, and it had some water on the outside, right there, so we'll add some water molecules. It has 4 oxygens attached, or interacting with it, that will balance its charge. And that's good. But could we have, say, maybe a sodium ion do this? Let's draw up a sodium ion. So, sodium ion. And it cannot interact with both of these. It's too small. It can't interact with that one and that one at the same time. So it can never really get the 4 oxygens that it needs to balance its positive charge. So that's why sodium can't go through this channel. Only a large ion like potassium can. So we had our potassium ion going through. It started right here. Now it's going to squeeze through and go right here, and it's going to lose all its water. And at this point, it's just going to keep on going through. So it's going to be right there. And when it's past this first step, another one can come behind it and start interacting with it. So draw the red. And again, the water would just pop off as this one goes down, and as that one goes down again. So now, what it would look like is this, where this potassium ion is interacting with this oxygen, this one, and this one, where this one's interacting with this oxygen atom, this one. So our potassium ion still has 4 oxygens interacting with it. Now the reason it goes down is just because of concentration gradients. It just randomly bumps into this. So let's say you had some potassium ions floating around, and they have the water around it, but I'm not going to draw the water anymore. Let's say there's also some in here. It comes down to how often they're going to hit it. If you have one that, like if there's a lot over here, then the probability of this being hit by a potassium ion is highly likely, and it will follow down the trail. Where if there aren't too many over here, they'll just come over and diffuse away, and the chances of them coming back and hitting it is low. So that's a concentration gradient basis, but I'm not going to go too much into the actual concentration gradient basis. I'm just going in, why does it work for potassium and not sodium? And it's all about the water that is actually around each ion. And I just want to make that clear. Even though sodium is smaller, and it would seem like it could fit right here. So if I were to draw it, I think that's about this. So if I was to draw it, it can't interact with with all the water or with any of the oxygens attached to the wall. It can only interact with maybe one at the most, and that's not enough to counter its positive charge. Remember, oxygen is electronegative, so these are negative, but they have to be close to each other for them to cancel each other's charges, and these are slightly negative. I can't remember the symbol. Slightly negative. They're not actually fully negative. They're slightly negative, where this is a positive charge, this is a positive charge, and this is a positive. That's why you need 4 oxygens for our simplified case to balance out this fully charged positive ion. And let's pretend, for say some reason that we could even get water into this. We still probably could not get 4 oxygen atoms touching this. So let's just try it, see what happens. So we'll draw maybe one right there. Can't fit there, that's too tight. And maybe right there. But the oxygen doesn't want to be next to those, so at our most we maybe get 3, but it has to have 4 to be neutralized. Or else the positive charge is just, again, too strong, and it doesn't want to be just positive. It wants to be neutralized with a water layer around it that helps take away some of that positive charge. And that's more of just understanding how ions separate in water. So that's why sodium can't go through, but a bigger ion like potassium can. And remember, potassium fits very well in this. Very well, where it interacts with all the oxygens. And just to be clear, you can only have 2 potassium ions in this channel at a time. You can't have one right there, because now you no longer have 4 oxygen atoms for every ion. This one and this one are now sharing. And that just doesn't happen. So that is a potassium channel at its basic. The only thing I would add is that there are slight negative charges on the edges. Just slightly, like the edges are usually slightly negatively charged. And that's to try to get these potassium ions close to it, so that the chances of them actually hitting increases a lot more. So if you have a little negative charge, the potassium wants to be next to that negative charge. So that's something that's kind of neat. And that's pretty much all for this video.